Hi, it's time for another math easy solution. We're going to discuss more optimization examples. Basically, look at part 2 of the example series and look at minimizing, in this case, cost. Let's just look at this example. Example 2, a cylindrical can is to be made to hold 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. And basically, the dimensions to minimize it, well, let's just draw what the problem is. Well, we have a cylinder here. This is something like this, like a can here, and let's say it has a radius r and a height h. This is basically, we want to just get the radius and height for this can, but then when you manufacture it, you have to make this entire area here. So you have to basically, in this case, to minimize cost, we have to minimize the amount of material we use, and basically what that means, minimize the area of this can, because we have to make the sides, we have to make the top and bottom. So then the area, so let's just go area or surface area here, is equal to, well, 2 times the area of the top and bottom. The area of a circle is just pi r squared, and then we have to plus the area of this height here, and basically we have to go to the circumference of a circle, which is 2 pi r, and then times it by the height here. So now we have this area of this, but now it's in a function of r and h, and we want to basically minimize this area here to get the minimum cost. But to do that, first we want to get rid of this h that is in here, so we're only dealing with r. And to get rid of the h, well, we know that the cylinder can is made to hold 1 liter. Well, also 1 liter is also equal to 1,000 centimeters cubed. So we'll just work with centimeters here so that we could get basically the dimensions of r and h in centimeters. So now this one is equal to, well, the volume of the cylinder, and then the volume is just equal to pi r squared times h, or just the area times by the height, and that would be the volume. The area of circles, pi r squared, and times h. So now we have this. We could rearrange to solve for h. So h would be equal to 1,000 over pi r squared. So now we have this h, we could plug it in. Okay, so now when you basically plug the h inside the function, the area function, we're going to have a area as a function of r only. So then this would just equal to, well, 2 pi r squared plus 2 pi r times h, which is 1,000 divided by pi r squared. And then basically, just to simplify this one out, this would just be equal to 2 pi r squared plus 2,000 over r. These pi r cancels here. So now we have this function here. And the domain in this case, well, r has to be greater than 0, otherwise we're going to have a negative area, which doesn't make sense in real life. And also, it can't be 0 here, and also it can't be 0 in real life. It can have an area 0. So then our domain here is just defined for everywhere greater than 0, so that's where the domain of this function is. And now to find out, basically, when this is minimum here, we have to find the critical points, and basically see how the graph looks like. So we have to find out critical point, and a critical point is basically when the derivative is equal to 0 here. Well, let's just solve for the derivative. That's going to be, this is a derivative function of r, is going to be 4 pi r using power rule, then minus this one using power rule as well. You could work this one out, negative 2,000 over r squared. We could simplify this further by timesing by the common denominator and top and bottom on this side, so r squared. We're going to be left with now 4 pi r cubed minus 2,000 all divided by, this one's going to be r squared. So now this one, you could just take the 4 out. This will just be equal to 4 and then pi r cubed minus 500 over r squared here. So now here, basically when we set this to equal to 0 here, if we set it equal to 0, we're going to have basically this one, 4 pi r cubed minus 500 times r squared. And this is only 0. Basically this cancels out, these cancel. It's only 0 when pi r cubed minus 500 is equal to 0, or simplifying this one, you're going to have r is equal to 500 divided by pi, and then this one is root 3, yeah, basically root 3 here, or you could just write this as 500 divided by pi to the power of 1 over 3. And when you plug this into a calculator, this is roughly 5.42 centimeters. So it's roughly around this one. We'll just work with this exact number right here. So now we have to see how the graph of A looks like to see if this is actually a minimum. And to do that, we have to check our local maximum minimum test, basically. Well, we have to see, well, if we just draw this x value here, let's just call this R, and this one is A. So then in this case here, this is the critical point here, let's say 5.42. So we just have to check on this, in this case here, this interval here, and this interval to see if it's increasing or decreasing here. So in the first interval for R is greater than 0, less than, basically let's just call it 5.42, etc. Then we have to see if this is increasing. So we look at this function here, and when we look at this one here, this r squared is always going to be positive here. This 4 doesn't affect it. But this pi r cubed minus 500, well, if this number is close to 0 here, this is going to be, then this number cubed minus 500, this is going to be negative. So in this case, we're going to have AR is less than 0, or it's decreasing. Yeah, so we have it decreasing. Now if we look at the second interval here, where R is basically just greater than 5.42 in this case, and as you can see from here again, you can see that it is when this one's always positive, and this one here, this is going to be a really large number. The minus 500 doesn't really affect it, so it's going to be positive. So then this is going to be basically when it's greater than that, it's going to be increasing, greater than 0 or increasing. And if you have this, the graph would just look something like this, because you would have it somewhat decreasing and then increasing. So this is the minimum here. So this is the minimum, and basically this is our dimension for radius. And thus, yeah, the A is minimum when the radius is equal to 500 divided by pi to the power of 1 over 3. So basically this is our dimension, and then solving for h, well, we know h is just equal to 1000 over pi r. In this case, we're gonna get, pi r squared, and in this case, we're just gonna get here 1000 divided by pi. This is gonna be a 500 divided by pi 2 over 3. And basically, we can simplify this further by just a neat little trick here. Just make these into the like terms that are inside this 2 over 3 power. So we're gonna have 2 times 500. And then basically divided by pi, and then basically just split this up. We're going to get 500 to the power 2 over 3. And then this is going to be divided by pi over 2 over 3. So now we can subtract this from this. This one we'll consider it as a 3 over 3. And this also is a 3 over 3. So we could subtract powers. You can see my video on the link below on how you could do this. Basically, you're going to have here 2 times, well, 500, this one's going to be 3 over 3, minus 2 over 3, this is going to be 1 over 3. Divided by this one, same thing, they're going to be 1 over 3. And this is going to be equal to 2 times, we'll put these together, it's the same power, 500 divided by pi 3, or 2, and this is going to be 500 divided by pi to the power of 1 over 3. And this just equals to r. And this just equals to 2r. So then h is equal to 2r. And this basically, yeah, this is our dimensions here. And then we just put all together here. Basically, r is dimensions to minimize costs is 5.42 centimeters. And then h is 2 times r to 10.84 centimeters here. And also, just to confirm this, we'll just graph this equation here, the function of a. So we just put it up with Google here. We're going to get 2 times pi times, well, r squared plus 2000 divided by r. Well, actually, yeah, you can't use r in Google for some reason. Let's just put x here. Okay, so now when we use x, there is r. So we have this function here. As you can see, we ignore the left side because we can't have negative area here. So as you can see here, how it's infinity, it's decreasing everywhere here, and then all of a sudden at this point near basically around 5.24, I think. So somewhere around here, as you can see, it's a minimum area. and then from here the minimum area is around 5.53 or something, and it keeps increasing and increasing. So yeah, that was the critical point. This is the minimum area, and basically that's how to minimize costs. So you could also always prove it with Google there. I mean, Google graphing. Well, that's all for today. Hopefully you learned, and I'll stay tuned for another math easy